Uh, Hello everyone, welcome to Q Physics Academy. This is our part 3 for Jest 2024 PIQ solutions. In this lectures, I will discuss question number 15 to question number 21. Not 21, not 21. We are discuss here. We are discuss here 25. Question number 25. So after this videos, I will complete the part A. Part A total 25 questions. Okay. If anyone not saw those videos, part 1 and part 2, for Jest PIQ series, please go there and saw these videos properly and note down the proper solutions each and every questions, then come here and then again enjoy these part 3 sections. Okay, then again enjoy these part 3 sections. Okay, so myself Mithun Patro, I am an PhD scholar at NISER's ACPS. I am actually working in exoplanetary formations and atmospheric model. So now let's start our videos. So okay, this is the question number 15. So in questions, what is the right sequence of optical component? What is the right sequence of optical component? Convert unpolarized light into a circularly polarized light. We already know unpolarized light. What is the meaning of unpolarized light? Unpolarized light, we have considered a light source, and that light source can emit unpolarized light, which means which has no specific directions. So it is considered as a light source, and it is emit light in a almost all directions. So this is the unpolarized light source. Okay, unpolarized light source. So from this unpolarized light source, we place here one polarizer and then place here another polarizers. Okay, then place here another polarizers. So first of all, from options A, here placed linear polarizer and then place quarter wave plate. So then what happened? We know what is the meaning of linear polarized. Linear polarized is a filter that only linearized the light when it passes through. It means if we consider an electric field, okay, if we consider an unpolarized electric field, okay, it's a component Ex plus Y cap, unpolarized. When it passing through is linearly polarized, then this directions of electric field is linearized in a particular directions. So it is like only a particular directions, either x directions or either y directions. And then when this linearly polarized light passing through quarter wave plate, then what happened? Okay, then what happened? So actually quarter wave plates in a quarter wave plate, actually what happened? Okay, in quarter wave plate, what happened actually? In quarter wave plate, there is a phase change. How much phase change actually occurs? In quarter wave plates occur phase change 90 degree of the x component and y component, right? the x component and y component. So what is the meaning of quarter wave plate? When the linearly polarized light passes through a quarter wave plate with axis at 45 degree to the polarization directions, the light is converted into circularly polarized light. How it is possible actually? So let us take an mathematical example to understand this. Okay, now let us, this is consider a unpolarized light, and this unpolarized light passes through a linear polarizer, and then this linearly polarized light passes through quarter wave plate. What happened? So let us consider an unpolarized light. Let us consider electric field is an unpolarized light. It's have a two component, Ex x cap plus Ey y cap. When this unpolarized light passing through linearly polarized light, then we get linearly polarized light, and that is nothing but E not x cap. That is, light is polarized along a particular directions. Okay, so linearly polarized light allows only one component of the electric field. So what happened? Linearly polarized light actually allows only one component of electric field, one component. Okay, linear polarized only allow one component. So okay, then this linearly polarized light passing through quarter wave plate. What happened? In this quarter wave plate, introduced a phase difference of pi by 2. So this quarter wave plate introduce phase difference of pi by 2 between the x and y component of the electric field. Y component of electric field. Introduce a phase difference. So then what happened? When this introduce this phase difference, then we get output like that, E0x x cap plus E0y y cap, where E0x nothing but E0 cos 45 degree into x cap plus E0 sin 45 degree y cap. So that is nothing but E0 upon root 2 x cap plus E0 upon root 2 y cap. So finally we are get E0 upon root 2 x cap plus y cap. So after, when this unpolarized light passing through linear polarizer, and then this linearly polarized light passing through quarter wave plate, we get a electric field like that. Output electric field is like that. Okay, E equals to E0 by root 2 x cap plus y cap, and this is nothing but a circularly polarized light. So for production of circularly polarized light, the right sequence is light source, unpolarized light source, then linearly polarizer and quarter wave plate. If what happened, this is considered a unpolarized light source, and then linear polarizer, and there is a half wave plate. Okay, there is a half wave plate. Then what happened? if there is half wave plate cannot create circularly polarized light from this unpolarized light, because half wave plate is actually rotates the polarization direction. Okay, half wave plate rotates the polarization directions clockwise or anti-clockwise. Okay, if this is clockwise, if this is clockwise, then half wave plate it rotates the direction of polarization, it will be anti-clockwise. Okay, rotates the polarization directions. And quarter wave plate introduce phase difference between electric field. So for please remember this sequence from unpolarized light to circularly polarized light. The correct sequence is unpolarized light source, linear polarizer, and then quarter wave plate for getting unpolarized light. Okay, unpolarized light. Please remember. And half wave plate, why half wave plate used for? The rotate the polarization directions. It's mean from counterclockwise to clockwise directions, clockwise direction to anti-clockwise direction. For that case we use half wave plate. Okay, so this is the current sequence for the creating circularly polarized light from unpolarized light. Okay, next we go to another questions, that is question number 16. It is very easy questions. Where does the Fermi level of n-type semiconductor lie? Where does the Fermi level of n-type semiconductor lie? So here the schematic energy band diagram, this is the for p-type semiconductor and this is for n-type semiconductor. Okay, and this is for conduction band. Okay, this is for conduction band, this is for valence band. Similarly for this is conduction band and this is for valence band, and this is nothing but a Fermi level, Fermi energy level. Again this is nothing but the Fermi energy level. Okay, for n-type semiconductor the Fermi energy level, the Fermi level is actually lie near the conduction band. Okay, near the conduction band minimum, near the conduction band, near the conduction band. This is very easy questions. So please remember, please note down, it is very important. This is like a theoretical questions. This is very easy questions. I think this is the in 2024 this is the most easy questions in Jest examination. Okay, next we go to the question number 17. This is very important questions. Okay, this is very important questions, and these questions asked from optical fiber. Each year they ask from this sections, optical fiber sections. Okay, so what is the questions? Is step index optical fiber have a refractive index n1 for the core regions. This is the core, regions, and n2 1.4 for cladding region. This is the cladding region, and this is also cladding regions. Okay, a ray of light is incident from air, this is the air region, here into the core. Okay, light incident on air into the core through a cross sections of the fiber at an angle theta with the normal. What is the limiting value of theta? Okay, what is the limiting value of theta below which the light ray will be totally internally reflected? Okay, what is the limiting value of theta? So for calculations, for these calculations First of all, we calculate the numerical apertures. Of the optical fiber, because from numerical apertures and this and this uh, and this acceptance angle, actually this angle is called acceptance angles. Okay, this angle is called acceptance angles. So expectance angles and the numerical apertures of the optical fiber have a relationship. Okay, so first of all, we calculate the numerical aperture for optical fiber. The numerical apertures of an optical fiber, actually it is the measure of the maximum angle at which a ray can enter the fiber and still experience a total internal reflection. Okay, so this is the angle, and this angle have a maximum value, and for which the light will experience total internal refractions. Okay, and this numerical aperture or this maximum value of this angle is related to the refractive index of cladding and core, and this is the relationship. N1 is the refractive index of core, N2 is the refractive index of cladding. So after putting this value of N1 the refractive index of core, N2 refractive index of cladding, and we get the numerical aperture is 0.112. Now we calculate the accepted angles or acceptance angle, and then accepted angles. Okay, the accepted angle, what is the accepted angle? The expected angle theta is the maximum angle in the air. Okay, maximum in the air. Numerical aperture is the maximum angle at which the ray can enter the fiber. Okay, enter the fiber and still experience the internal reflections. Or the expected angle is the maximum angle in air at which light can enter, the core and still guided. Okay, still guided. So numerical aperture and accepted angle. Numerical aperture is the maximum angle at which ray can enter the fiber and still experience total internal refractions, and accepted angle is the maximum angle in the air at which light can enter the core. Okay, light can enter the core and still be guided. So it is related to numerical apertures, accepted angles and numerical aperture related to. So that is equals to sin theta equals to Na. There is a relations. So theta equals to sin inverse Na, and then we finally get the value 6.229. So please note down this relationship, this accepted angles and numerical apertures. What is accepted angles, what is numerical apertures, and their relationship? That is the question actually. Okay, and okay, so we get finally 6.229. So option is the correct answer. Okay, so option is the correct answer. Next we go to the question number 18. A satellite of mass 2000 kg is placed in an elliptical orbit around the earth and semi-major axis A, capital A. Assume that the total energy of the orbiting satellite is E and the angular momentum is capital L. Okay, and through a series of maneuver, the elliptical orbit is changed to a circular orbit with a radius capital A. Okay, with a radius capital A. So for the orbital change is described by this following. मतलब एक satellite first revolve in elliptical orbit, and after some series of maneuvers, this elliptical orbit is changed to circular orbit. So from this elliptical orbit to circular orbit. So for this change, this is elliptical orbit, and this is circular orbit. And this elliptical orbit have a semi-major axis is capital A, and circular orbit have a radius is capital A. Okay, so for energy So for this change, what will be changed? Total energy of the satellite or angular momentum? What will be the change? So we know the total energy of satellite when it is revolved around elliptical orbit is equals to minus G capital M upon 2a. 2a is the semi-major axis, and then when it is revolving in circular orbit, then its survey energy is same, right? So for when a satellite moving in a elliptical orbit and this elliptical orbit converted to circular orbit, then energy does not change actually, okay? Then energy does not change. Please remember, energy have a same formula, energy does not change. But what happened for the case of angular momentum? So when a satellite moving in an elliptical orbit, then it's have angular momentum L small m root under G capital M A 1 minus square, where E is the orbital eccentricity and A is equals to capital A, and this is nothing but the semi-major axis. Semi-major axis. And when this orbit is changed, converted to circular orbit, and for circular orbit E will be 0. So when E equals to 0, and then we get the angular momentum, nothing but m root under capital G capital M capital A. So this is nothing but like that. So finally we get for elliptical orbit we have angular momentum small m root under G capital M capital A 1 minus square, where E is the greater than 0, and for circular orbit we have angular momentum small m root under G capital M capital A. So from these two expressions we get the angular momentum of circular orbit is greater than compared to the angular momentum of elliptical orbit. So when the orbit will convert it from elliptical to circular orbit, angular momentum must change, okay? Angular momentum must change. So please remember when elliptical orbit change to circular orbit, energy does not change, total energy does not change, angular momentum change, okay? Angular momentum change. Please remember these 2 points. It's very easy questions. Okay. Next we go to the next questions, that is question number 19. So this question number 19, this is for your homework questions. Please do yourself. This is the homework questions. And send the solutions in our WhatsApp group. I will check. I will guide you what is the this solution is wrong, right, okay? And similarly for question number 20, it is also a very easy question. This is also your homework questions. This is also your homework questions. So from 25 questions, I will give you the solution for 23 questions, but you do by self only 2 questions, okay? You do by self by only 2 questions. Question number 19 and question number 20 is your homework questions. Question number 20 is a very good, very easy questions. If anyone follow my theory lectures for op-amps, he or she definitely do it, okay? So question number 19 and question number 20, this is your homework questions. Please do by self. And now next go to the question number 21. Question number 21. Given that the latent heat of liquefaction is 80 calorie per gram, that is L equals to 80 calorie per gram, what is the change in entropy when 10 gram of ice at 0 degree centigrade is converted into water at the same temperature? So here 10 gram of ice at 0 degree centigrade, it is converted to water at same temperature. So here temperature is fixed. What will be changed? Ice changed to water. So there actually occurs a phase change. So there actually occur phase change. Okay. So there actually occurs phase change, right? So for phase change, for this phase change, what amount of energy is required? For this phase change, what amount of energy is required? That is nothing but ml. We know already. For phase change, what amount of energy is actually required? ml. For temperature change, what amount of energy required? mst, right? mst. These two equations are very important for your competitive exam purpose. Here temperature is fixed, only phase change occurs. For this phase change, what amount of energy required? That is nothing but ml. M is the mass of this mass, and L is the latent heat of liquefaction. So to calculate the change in entropy when 10 gram of ice at 0 degree centigrade is converted to water at the same temperature, that is change in entropy for only phase change. Okay, so for phase change, change in entropy is nothing but delta Q upon T. Delta Q is the heat absorbed or released during phase change. T is the temperature at which the phase change occurs. At what temperature phase change is actually occurs. So for so here this is the value of heat absorbed for phase change. For phase change, that is nothing but ml. M is nothing but 10 gram. L equals to 80 calorie per gram, and T equals to actually 0 degree centigrade plus 73 Kelvin. So this is equals to 73 Kelvin. 0 degree centigrade, at 0 degree centigrade temperature the phase change actually basically occurs. So that's why the value is equals to 0 degree plus 273. So finally we get the change in entropy is equals to 2.93 Kelvin. Okay, 2.93 Kelvin. So this is very easy questions. So from this question we get option A is the correct answer. Okay, next we go to the another question that is also very important. Okay, consider a system of n non-interacting spin half atoms subjected to a magnetic field with Hamiltonian. There a Hamiltonian is given, right? So there is a Hamiltonian is given minus G mu B magnetic field summation over I1 to n Sij, where G is the dimensional Landesi factor, mu B is the Bohr magneton, B is the strength of the magnetic field, and Sij is the jet component of the spin of the ith atom. Jet component, where Sij jet component. Spin of ith atom. Okay, ith atom, and its have a value plus minus half. Okay, please remember. And the system is in equilibrium at temperature T. What is the probability? That the jet component of spin corresponding to two given atom, please remember, corresponding to two given atom have the same value. It means what actually they asked, probability of finding the particle for the finding the atom have the same spin value. If we take two atoms, they have a spin plus up. Either we take a atom, they have a spin minus up or minus up. For this case, what is the probability? Okay, so next how to calculate. So here the Hamiltonian of the system. So energy of a single spin, let us consider a single spin, only single spin, not consider n number of spin, we consider only single spin. For single spin, the energy is nothing but minus g mu b b Sz, and Sz have a plus up, then energy is nothing but minus half g mu b b. When Sz have a value minus half, then energy is equals to plus half g mu b b b. Next we calculate probability distributions. The probability of a single spin being in a state with Sz equals to plus half or Sz equals to minus half. We consider a single spin for single atom. For single atom, and this atom have a spin in a state Sz equals to plus half, then what is the probability? And for a single atom, and this atom have a spin Sz equals to minus half, then what is the probability? So probability when Sz equals to plus half is equals to, this is the formula of probability, e to the power minus beta e plus upon z. Okay, so let's substitute this value here, e plus, and we get the probability. Similarly, probability when a single spin being in a state Sz equals to minus half. Okay, so that is equals to e to the power minus beta e minus, and put here the value of e minus, and then we get the probability. Okay, where z is the partition function, right? So partition function, this is the formula of partition function, and we substitute here the energy, and that is nothing but E plus, and that is nothing but E minus. Okay, these two values are E plus and E minus, and this is the partition function of the given system. Now calculate the probability of the same spin of two atoms. Probability of the same spin of two atoms. The probability for Sz equals to plus half. It means two atoms have a same Sz value. So probability from Sz1 half and Sz2 half for one atom. This is the atom number 1, and this is for atom number 2. Okay, and this case, this is the probability for S1Z half, this is the probability for S1Z half. So finally we get e to the power, so this is nothing but e to the power g mu b b upon 2 upon z whole square. Similarly, for probability for Sz equals to minus half, that is nothing but e to the power minus beta g mu b b upon 2 upon z whole square. Okay, this is the probability of the probability when for Sz equals to plus half for two atom, probability for Sz equals to minus half for two atom. This is for two atom, for two atom. Now the probability that the two spin are the same, probability that the two spin are same each. This is very easy question, we just add these two. So probability for same spin for two atom, same spin for two atom, probability for same spin of two atom. This is the probability for two atom having Sz value plus 1, and this is the probability for two atom having Sz value plus 1, and this is the probability for two atom Sz value minus 1. And next we just simplify this equation, and here we substitute the partition function value. After substitute this partition function value, we get e to the power partition function value, and rearrange this. So finally we get this result. Okay, finally we get this result. So this question is very easy question, you just understand the meaning of this line, what is the probability that z component of spin corresponding to two given atom have the same value? You just clearly understand. Okay, if you understand this line, you definitely solve this problem. Okay, when you solve this problem, please mark down in your copy. This is the important line. When you anytime see this line, you definitely when you see this line, and then it's it's obviously click your mind, okay, what actually I am doing. Okay, so the z component of spin corresponding to atoms have the same value. What is the probability that the z component of the spins corresponding to given atom have the same value? Probability for same spin, that is probability for two atom having spin Sz equals to plus half plus probability for two atom having spin Sz equals to minus half. So that is equals to Sz1 half Sz2 equals to half plus probability for Sz1 equals to minus half Sz2 equals to minus 1. This is the actual formula of these questions. Okay, you just solve it. Okay, next we go to the next questions, that is question number 23. Next we go to the question number 23. Two electrons have orbital angular momentum quantum number L equals to 3 for one electron, which is for one electron, and L2 equals to 2 for other electron, respectively. Okay, let LZ equals to LZ1 plus LZ2, where LZ1 and LZ2 are the z component of respective angular momentum operator of two electrons. Okay, so how many linearly independent states have LZ quantum number m equals to 2? How many linearly independent states have LZ quantum number m equals to 2? So we know for LZ have a quantized value, m number of quantized value, So m have a value minus L2 plus L, and where L is the orbital angular momentum quantum number. Orbital momentum quantum number. So for electron 1, with L1 equals to 3, orbital quantum number is 3, then M1 L for LZ1, the number of quantized value M1 have a value from -3 to +3, because minus L to plus L. So M1 have a value -3, -2, -1, 0, +1, +2, +3. This is for LZ1. This is for LZ1 quantized value. This is the quantized value for LZ1. LZ1. Similarly, for electron 2, when orbital quantum number is 2, then this is the quantized value for LZ2. Okay, these two are the quantized value for the fixed orbital quantum number for L1 equals to 3 and L1 equals to 2. Now they ask how many linearly independent states we get for LZ when M equals to 2. M equals to 2. Where M is nothing but M1 plus M2. Where M is nothing but M1 plus M2. Where M is nothing but M1 plus M2. Okay. So we get M1, that is value -3, -2, -1, 0, +1, +2, +3. We get M2 -2, -1, 0, +1, +2. So we trying to find out the value of M equals to 2 for the combinations of M1 and M2. So we get how many combinations of M1 M2 and we get M equals to 2. This is the questions actually. So they ask how many linearly independent state have a LZ, having LZ. It means M equals to M1 plus M2 value. M1 plus M2 value is equals to 2. M1 plus M2 value is 2. So we get how many state? We get M1 plus M2 value equals to 2. So here we get the combinations when M1 equals to 2, M2 equals to 0, right? M1 equals to 2 and so 0, then we get 2 value. When M1 equals to 3 and M2 equals to -1, then we get 2 value. When M1 equals to 1, M2 equals to 1, then we get M1 plus M2 equals to 2 value. Again M1 equals to 0 and M2 equals to 2, then we get 2 value. So we get 4 independent state. Having LZ quantum number M equals to 2. So 4 independent state have a LZ quantum number M equals to 2. So please understand the questions, what actually they ask. Okay, so for this question we get option A is the correct answer. Okay, next we go to the question number 24. This is another very good questions. Okay, so a quantum particle is subjected to the potential V of x equals to ax plus bx square, where a and b are the constant. What is the mean positions of the particle in the first excited state? You just notice here the potential V of x equals to x plus bx square. This is a linear potential, linear term, and this is quadratic term. Means this potential for SHM. Okay, so for we know the for SHM the potential structures is looks like that, right? But here this linear due to this linear term, the equilibrium positions must be shifted to a particular point. So this from this potential we get a one concept. There is a linear potential plus simple harmonic potential. Okay, and simple harmonic potential have a equilibrium positions, but due to this linear potential, the equilibrium positions of simple harmonic oscillator must be shifted. Okay, this is the concept. So first of all, we calculate the equilibrium positions for simple harmonic oscillator. Equilibrium positions for this from this potential. So we get the equilibrium positions at x equals to a minus 2b equilibrium positions. So this is the positions or the potential is actually minimum, and it is corresponding to the equilibrium positions of the particle. Okay, it's fine. In the first excited state of the harmonic oscillator, the wave function is symmetric around the equilibrium positions, obviously. But because of the linear potential, the shift causes by this linear term x, the expectations value of x will be the equilibrium positions. Please remember these points. Because the shift causes by the linear term, the expectations value of x will be the equilibrium positions. So equilibrium position x equals to a minus b. Thus the mean positions of the particle in the first excited state, this is nothing but a minus a upon 2b. So please note down this point and understand what actually they ask. Okay. Next we go to the question number 25. This is very good question. The density of state of a system, which is given, where h cut is the Planck constant, omega is the natural frequency of the system, taking kb is the Boltzmann constant. Compute the temperature of the system. Okay, so we have the density of state of the system of n particle with energy is given by 1 upon h cut to the power n e to the power n minus 1 upon n minus 1 factorial for e greater than 0 and 0 for e less than 0. And we have the thermodynamic relations between temperature and entropy 1 upon T 1 upon delta S upon delta E. S is the entropy of the system, E is the energy of the system. Now we have the relations between entropy and the number of microstate is equals to Kb ln omega. Omega is the number of microstate at energy E. We know the number of microstate have a relationship with density of state. So number of microstate, that is omega E equals to integration 0 to E and density of state and dE. We just substitute the value of density of state minus h cut to the power n E prime n minus 1 and later take out the constant term, and thus we just simply integrate, and finally we get the number of microstate, that is equals to e to the power n h cut to the power n upon n factorial. So the entropy of the system is nothing but Kb ln 1 upon h cut to the power n e to the power n upon n factorial. Okay, now we just simplify this and we get entropy is nothing but Kb n ln e minus n ln h cut minus n ln n factorial. We just from this we use the Stirling approximation. Okay, Stirling approximation, that is nothing but ln n factorial suman ln minus n. We use this Stirling approximations. So this is the equation number 4. So now from this equation it is very important to calculate the temperature of the system. So from we have the thermodynamic relation 1 upon T del S upon del E. Now equation number 4, differentiate equation number 4 with respect to E. Okay, so that is equals to Kb ln. We get differentiate only this part only, other terms are constant term. Okay, so delta upon del E ln E, so kbn upon E, so temperature T equals to E upon kbn. So finally we get the temperature of the system E upon kb whole to the power n. So from these questions we get option E. So here if we have a density of state, how to calculate? Here a flowchart, have a given density of state to calculate temperature of the system. So temperature of the system, first we calculate the entropy kb ln gamma. Gamma is the number of microstate, and number of microstate have a relationship with density of state. Okay, and from this and then we calculate entropy, and from this entropy we calculate the temperature from this thermodynamic relations. Please remember this sequence, how to calculate from density of state to temperature of the system. Okay, so in this way we are calculate all the part A questions of Jest 2024. Okay, in the next lectures we proceed the another part, that is part B, 15 questions, and then we continue our lectures again in the similar way. Okay, so for thank you again, thank you for watching this video, and को आप लोगों को ये बात बताना है, please subscribe this channel and also keep watching these videos, and if anyone feel any kinds of difficulty, please comment in my channel. I definitely give you the suggestions, what is the solutions, what is the concept behind the formula, etc. Okay, and again thank you for watching this video. Please like and subscribe my channel. Okay, thank you.